In this video, we're going to derive the equations for mass and energy balance in a porous medium when we have multi-phase flow. So let's start off doing a general derivation in 3 dimensions using Gauss's theorem, and then I'm going to do it a lot more explicitly in 1 dimension, because that is the equation that we're going to solve later in subsequent videos. So imagine some arbitrary region of space, okay, like this. We will have a solid, we will be flowing porous media, and we will have in general fluids phase 1 and phase 2. Okay, so what we're going to consider is the change, first of all, in mass, but we're also going to do an energy balance due to a flux. So there is going to be some flux all around this general volume. So this general volume is enclosed in a surface across which is a flux. Now at this point, don't overthink the flux. In the previous video, we introduced this idea of flux being minus coefficient times a gradient of whatever it is you're interested in. So at this point, just pause. Don't think, what exactly is the flux? Just call it an F and see where we head. So what's going to happen? We have some mass within the volume, okay? And the rate of change of mass is going to be proportional to the flux. So if we have the mass in the volume, how it varies with time, okay, and that can also vary with space, so we use partial derivatives, is got to equal the integral of the flux over the surface. Okay. Now, we're going to get our units right if you're worried about this. Flux is generally going to be measured, for instance, in kilograms per square meter per second. So we integrate it over a surface, it's going to be kilograms. My mass is in kilograms per cubic meter. This is mass per unit volume here, integrated over the volume. That's going to be a mass. And then I'm looking at the rate of change. So the flux over the surface, but now I need to get my signs right. This is a minus sign, isn't it? Because if there's a flux out, if I have a positive flux that's out, my mass is actually going to go down. Okay, so now I'm going to use Gauss's theorem, and I'm going to convert this surface integral to a volume integral. So I can write this as the integral of div dot f over a volume. Okay, and then this I can take the derivative, the time derivative inside here, and we get this relationship. And of course this is true for any arbitrary volume. And so now I can write a sort of general form of a conservation equation by removing the integrals and saying the integrands have to be equal. So dm by dt, and then I'll put this over the other side, plus div dot f equals 0. So just to be clear, m is going to be a mass per unit volume. When we do energy balance, it's actually going to be energy per unit volume. And f is a flux per unit area. So this will be mass per unit area per unit time. When we do an energy balance, it's going to be in watts per square meter. Okay, so that's the general form. Very easy to derive, but I made this little trick with Gauss's theorem. For those of you not familiar with it, what we're going to do next is derive this equation in 1 dimension in a much more explicit fashion. So we derived the 3-dimensional version of the equation. Seems like a step back. I'm going to do the 1-dimensional version, for whom you already probably know the solution. So let's just write it down so that we know where we're heading. It's the change in mass per unit time plus the spatial derivative of a flux per unit area. And if there's no source or sink, that's equal to 0. But let's see where that equation comes from. So let's consider 1-dimensional flow in the x direction. That's what we're doing. And we're going to take some location x and we're going to take some arbitrary location x plus delta x. Okay, and so we can imagine a box here. Okay, and the box is going to have some cross-sectional area A. This cross-sectional area, by the way, is a dummy. It's going to, in the sense that it's going to cancel out in all the equations. Okay, so we have this box, and what we're going to do is we're going to have flow into the box and out of the box. So we have a flow in and a flow out, and this is going to have a flux, and this is the flux going out is at spatial location x plus delta x, and the flux going in is at location x. So what we have to do is we just need to keep track of mass and flux. And at the moment, we're just going to do this as mass per unit volume, flux per unit area. In the next section, we'll actually write down what they are for a specific case. Much easier to do this in general and then think about the specific case than to try and say, oh yeah, but this is a porous medium with these phases in, and how do I deal with it? Just imagine there's a flux, something's moving, and there's a mass. Okay, so we have a mass at time t, and then we have a mass at time t plus delta t, and it changes because what flows in and what flows out are not necessarily the same. So let's think about the mass. Okay, so the change in mass, okay, is m of t plus delta t minus m at t, okay, and that now needs to be multiplied by a volume, okay, which is a delta x. So that is a change in mass measured, for instance, in kilograms. This is a volume, this is mass, it's actually a density, strictly speaking, it's a mass per unit volume. So this is the change in mass, and this has to be equal to the flux in minus the flux out, so f of x minus f of x plus delta x. But remember, this is a flux per unit area, so multiplied by area, and then a flux, that's kilograms per square meter per unit time. So this is a time delta t, so I have to multiply this by delta t. Now I've got the units right. Okay, so this is mass, this will have units of kilograms, this will have units of kilograms. So now how do we deal with this? As I said, A is always a dummy, so you could almost do it per unit area. If you wish, a bit like my laws of transport and flow, all per unit area. I didn't sort of put an area in. I found that a bit silly, frankly. And what we're going to do is we're going to put the delta t here, down here. We're going to divide by delta t like this, and we're going to put the delta x down like that. Okay? All right? And then it really is f of x minus f of x plus delta x, because this is what goes in minus what goes out. So if a lot goes in, the mass goes up. If a lot comes out, the mass goes down. So we got the signs right, but what I'm going to do is I'm going to put it over this side of the equation, okay? So we flip the sign. So we end up with something that should look fairly straightforward here. We got m of t plus delta t minus m of t over delta t plus f of x plus delta x minus f of x over delta x, and that equals 0. And in good old calculus fashion, we're going to take the limit that delta t and delta x go to 0. And I think we can see that this is dm dt and this is df dx. And so I hope I don't have to write any more. You can see immediately that this reduces to this form. So in general, the equation is the rate of change, and this is mass per unit volume, is equal to the plus the spatial derivative of some flux per unit area is equal to 0. And we're now going to do two examples. We're going to do mass, but we're also going to do energy. So this could be the energy per unit volume, and this will be the flux of energy, right? Energy is conserved, mass is conserved. Fundamentally, the conservation equation is the same, and that's the emphasis here. I don't think, I do a conservation equation for mass, and then, for energy, it's completely different because energy is different, all the symbols are different. No, the fundamental equation is the same, right? Something, whatever it is, that's conserved per unit volume, the time derivative plus the spatial derivative of the flux equals 0. Now let's do a specific example, and we will start with a mass balance. So we said that we had a porous medium, and we have two fluid phases. So we have a solid and we have two fluid phases, 1 and 2. And what I'm going to do is mass balance for phase 1. So imagine I've got water and carbon dioxide flowing in a porous medium, or water and oil. And I'm going to do mass balance for water. And I'm also going to assume that there is no phase exchange. So water stays in the water phase, there's no mixing with phase 2, the other phase, and there's no interaction with the solid. I can break those approximations if I wish, but that's what I'm going to do just for this example. Okay, so let's think about the mass. This is the mass per unit volume of the whole porous medium of phase 1. Well, think about that carefully. Phase 1 is only in the pore space. So for unit volume, the volume of pore space is phi, the porosity. But phase 1 doesn't occupy all the pore space because there are two fluid phases in the pore space. So the fraction of the pore space occupied by phase 1 is called the saturation, S1. So that's the saturation. But just a moment, that's just a fraction. I want a mass per unit volume, so I have to multiply by the density, don't I? Okay. So the mass of phase 1 per unit volume of the porous medium, right? Because when we talk about volumes, we always talk about the whole porous medium, not just the pore space or not just the grains, is the porosity times the saturation times the density. Now, this is quite an easy example, but you could consider things that were more complex. You could have something, for instance, that was dissolved in the water, like carbon dioxide. So you could have then the concentration of carbon dioxide, and then you could have something absorbed to the solid, or you could something partitioned in the other phase, as long as you keep account of it. Again, this is just how much of a conserved species you have per unit volume, and you just have to keep track. That's all you need to do. So this is just one simple example, but there will be more complex ones. Now I need to know the flux. Okay, well, the flux is the mass of phase 1 flowing per unit area per unit time. Well, we know we got Darcy's law. Right, that's where Darcy's law comes in. Q1, this is for phase 1, will be the volume of phase 1 flowing per unit area per unit time. It's a volume. So I need to multiply it by density. Okay, so this is my volume per unit time per unit area. Multiply it by density, that's mass per unit volume, so it's mass per unit time per unit area. So it has the right units. So this example is really quite straightforward. Okay, so now when I have my equation here, which is dm by dt plus df by dx equals 0, or if I want it in 3 dimensions, this second term would be the divergence of f. Then I can put this in here. I got phi s rho q rho, so I get d by dt of phi s1 rho 1 plus, in one dimension, d by dx of q1 rho 1 equals 0. Now, that looks fairly straightforward, but now I'm going to make another approximation. And it's a specific approximation that I'm going to use for the development of analytic solutions. I'm going to assume incompressible flow. Now, this is a good approximation in many examples, certainly in experiments where I got a little piece of rock and I'm injecting one fluid to displace another, for instance. At the large scale, at the reservoir scale, if we have fluids at very high pressures and reasonably dense phases, although there will be changes in pressure and changes in density, those changes are relatively small. So when we're in this case, we can assume incompressible flow, and we will assume two things. One is that the density then is some constant value, and also by injecting the fluids, I haven't altered the pore space, so the porosity remains constant. And if that happens, then density comes out, right, of the equation and disappears. Porosity comes out, and in fact I write my equation in this way. Okay, and this is the equation that actually in subsequent videos we're going to solve analytically. Now, it looks very simple. We could almost have derived that from scratch without having to do the M and the F. Q is going to be given by Darcy's law, so remember that we have a little bit of a complexity here. We're going to have a gradient in pressure coming up. But I just want to mention the major approximation here. The other direction in which we can go with analytic solutions is to assume that we only have single phase flow, or one phase is flowing. So in this case, the saturation is constant, okay? And so the saturation is the one that comes out, and we end up with an equation for changes in density. And if we have a compressible fluid and a relationship between density and pressure, we actually end up with a diffusion-like equation for pressure. And that's solved routinely in pressure transient analysis, and something that is the subject of another course. But for this analysis, we're going to assume that the density and porosity are constant. And now this is an equation for displacement, how the saturation changes as one phase displaces another in a porous medium. Now we're going to derive an energy conservation equation. So we're going to do energy conservation, conservation of energy. And we're going to end up with an equation for temperature. So before we did mass conservation, we ended up actually with an equation for saturation. Here for energy balance, we're going to do temperature. So this one is a little bit more complex, so we need to go through it step by step. So imagine we got fluid 1, we got fluid 2, and this time we also have the solid S, and all three of those phases, right, contain energy. The energy here is going to be thermal energy. So let's think about thermal energy. How would we go about quantifying that? Well, if we have a substance with a heat capacity C, let's just think carefully about the units of C. C can be defined in different ways. I'm going to have it as joules per Kelvin per kilogram. Okay, so that's the heat capacity. If I assume the heat capacity is constant and multiply by temperature, then that's joules per kilogram. But remember, I want mass per unit volume, don't I? So of course I multiply by density. So if I multiply by density times a heat capacity times a temperature, I'm going to have something that has the units of joules per cubic meter. So that's energy per unit volume. So that's what I want. So C here is going to be, it's a small c, this is heat capacity. So my M, if you recall, my M before when I was doing mass balance was mass per unit volume. Here, you know, sometimes people say, no, if you've got an M, I'm getting myself confused, okay? Let's call it E, right? So this is the energy, or the thermal energy. I'm only going to consider thermal energy, right, per unit volume. So this has units of joules per cubic meter. Okay, so now let's do the thermal energy. Okay, so phase one, right? All three phases have thermal energy. I can't just say, oh, let's just look at the energy balance for phase one. No, heat doesn't work that way, right? As you know, heat will transfer between the phases. I can't make that as an assumption. Okay, so let's think about phase one. Per unit volume. What about the porosity? Because per unit porous medium volume, just as we did with mass, there's only a fraction phi that's pore space. But phase one doesn't occupy all the pore space. If we have two phases, that's the fraction of the pore space. So that's the fraction of the pore space occupied by phase one, and then its area is given by this, rho 1 C1 T. And we'll assume that the temperature, however, in my arbitrary volume, because it can be an infinitesimally small volume, is the same in the three phases. So phase one, phase two, and the solid all have the same temperature, but they obviously have different saturations and different properties. So that's phase one. For phase two, it's going to be the same, phi S2 rho 2 C2 times temperature. And then we also have the solid. Well, if phi is the fraction of the volume that's pore space, 1 minus phi needs to be the fraction that's solid. So this is the solid fraction. And then we need to do CS. We don't have a saturation of solid, okay? And then temperature, and then of course I've left out. Okay, so that's your energy. Now what about your flux? Now that, if we recall, is in watts per square meter, or joules per second per square meter. That's your flux. Now the flux actually has two components. So we do need to think about this a little bit more carefully. And one of the components we haven't sort of mentioned. So we did heat conduction. We did Fourier's law, right? So there's conduction, right? F is minus kappa grad T, if you recall. But that's not all, is there? If fluids are moving, there's also convection. So imagine I've got hot water that I'm injecting, and that hot water is moving through the pore space. That's delivering energy, isn't it? So convection. How do I think of the flux due to convection? Well, again, it comes from Darcy's law. If we have a flow of fluid Q, that's a volume per unit area per unit time. Now, if I multiply by density, that's a mass, okay, per unit area per unit time. And what energy does it deliver? It has this energy CT. So convection, okay, is the delivery of heat due to movement. And it's proportional to Q from Darcy's law, because that's the volume flowing per unit area per unit time. So let's do this in SI units, right, per unit time. We've got a density, which is kilograms per cubic meter. We have our heat capacity, which we know is joules per Kelvin per kilogram. And we got our temperature, in Kelvin. So if we look at the units there carefully, okay, we got joules per second, kilograms go. We've got joules per second per square meter, joules per second per square meter. So that has the right units and the right physics. So the convection now is given by this, and the conduction, and we simply add the two, right? So we have this plus this. But now we have to do that for all three phases. We have solid, we have phase 1, and we have phase 2. So we need to go through that, and we need to do that carefully. In the solid, there's only going to be conduction. The solid doesn't move, but the two phases, both of them move. So if we look at the convection term, there's going to be Q1 rho 1 C1 plus Q2 rho 2 C2 times temperature. Okay, so this is phase 1 and this is phase 2. Okay, the solid doesn't move, so there's no convection term for the solid. For the conduction term, there's conduction in all of the phases. Now, how do we deal with the conduction? There's an addition to the flux, but there's a minus. How we view this traditionally is we don't just write K for the solid times grad T, because we say, well, the solid isn't the whole volume. It only occupies a fraction 1 minus phi. So what we have to do here is we traditionally multiply this coefficient by 1 minus phi for the solid and by phi when we're treating the liquid. And it's the same as what we did with diffusion. In a porous medium, we multiply the diffusion coefficient by porosity to look at the restricted volume. So traditionally, how the conductive flux would be written is minus 1 minus phi times the heat conductivity of the solid, and it's all minus phi times S1, because it doesn't occupy all the pore space. It's not just a porosity factor, times the conduction of phase 1 minus phi S2 kappa 2. Okay, so that's the conduction, that's the convection, and we're actually going to add all of those terms together. That's your flux, okay? And then this is your energy. Now, at this point, it's all getting a little bit messy. So maybe the best way of dealing with this is to write this out again and then show the final form of the equations in their simplest form. And we are going to make some additional assumptions as well. Okay, so let's write out the equations again, just so that we can go step by step. We have the mass, which is not a real mass. It's an energy per unit volume now. Okay. And we need all the components there. And we have the solid. This is the amount of solid, density of the solid, heat capacity of the solid, times temperature. And I'm going to put temperature at the end because this is all proportional to temperature. Then we have a porosity times density 1 C1 plus phi rho 2 C2. And that's all going to be proportional to temperature because this is just thermal energy. Okay, now we have the flux, and the flux, the heat flux had two components. It had convection and conduction. So convection is just the fluid movement. So this was just with the fluid phases. So it was Q1 times rho 1 C1 times temperature. So I'm going to again just put this as proportional to temperature. Q2 rho 2 C2, and this is proportional to temperature as well. It's a flux that's proportional to temperature and proportional to basically the amount of fluid that's flowing. Then we have, so this is convection. Then we have a number of terms minus, and they're all going to be multiplied by grad T. So I'm going to put the grad T at the end. This is the heat conduction. Okay, so there's going to be 1 minus phi, okay, times the solid, plus phi S1 times phase 1, plus phi S2 times phase 2, and this is all going to be grad T. Okay, so that's conduction. Okay, so the equation is, let's write it in terms of E, right? dE by dt plus dF by dx is equal to 0. Now, in general, this is going to be quite complex because we got temperature here, and obviously we're interested in variations in temperature if we're looking at heat transport, but we've also got fluid flow. So in the previous example, I just looked at conservation of mass. I didn't consider energy at all. I didn't consider temperature. I actually assumed that the fluid properties were independent of temperature because I had a fixed, if you noticed, I had a fixed density. I'm going to do the opposite assumption here simply because I then have an equation that we can deal with. So for this example, just so that we can show the effect of heat transport, I'm going to assume that we actually have fixed saturations, okay? And we also have fixed densities. So S1 and S2 stay the same. So let's imagine it's steady state flow. So we have the two phases flowing. Or maybe a simpler example is we just have water flow, but we have hot water, say, displacing cold water, in which case S2 is 0, S1 is a constant. We're not going to allow for there to be significant changes in density either. We're just going to assume that the heat conducts and convects. Okay? So we're going to assume these are fixed, and then we're going to write this as an equation for temperature. So I think the easiest way of doing it, rather than write down this bunch of terms over and over again, is to write this equation in its final form, show why it is, and then the various terms in it. So what we can do is, in the end, the only thing that varies here is temperature. I'm going to assume all the other coefficients, heat capacities, conductivities, and saturations, and for that matter, therefore, the fluxes associated, the Darcy fluxes associated with the phases are all fixed. So the only thing that varies is temperature. So we're going to get an equation for temperature. So I'm going to write it like this. So this is actually going to be my final equation. But you might say, well, what are these terms alpha and beta? Well, beta is going to be wherever there is just a dt dx. So it's wherever there's this t term, then this becomes dt dx. And then all of this, we're going to assume, right, all of this term, which we assume to be constant, is then dividing both sides. So beta, hopefully we can see, beta is just this that pre-multiplies the temperature. So it is just a bunch of terms. So don't, worry about this. And then it's going to be divided by this bunch of terms because we've assumed all of these are constant, right? So 1 minus phi. Okay, so hopefully you can see where that comes from. Then we have a grad t term, right? And this in one dimension is a dt by dx. And then we differentiate it again, so it's a d2t by dx squared term, so that's why we get this. But notice there's the minus sign, right? Because Fourier's law, high to low temperature, right? So I put this over the other side of the equation. And so my alpha is basically this bunch of terms and then divided by this bunch of terms before, right? So the same denominator here. So I'll just write this out. I'll do it reasonably quickly. right? And then it's just these terms. Okay. I don't want you to think too much about these terms. In a later video, we'll sort of talk about typical magnitudes of these terms. You can notice, you know, there's some things that seem to cancel, but this is really, fundamentally, it's a heat conduction divided by density times a heat capacity. And this alpha is therefore what's called a thermal diffusivity. It basically shows you how temperature diffusivity, how temperature diffuses. This, okay, we got densities here, heat capacities, so it really looks like a flux divided by some sort of porosity. So this actually turns out to have the units of meters per second and is in fact an effective speed. Now, if you can't see that, that doesn't matter because that's what we're going to go through in subsequent videos. But for now, just look at the structure of the equation. There's a time derivative here, then there's a spatial derivative, and this spatial derivative is due to convection. So temperature will change with time because, say, I'm injecting hot water and it's moving through the porous medium. Don't overthink all these terms look complicated. No, that's physically what's happening. It's just moving. Hot stuff is moving through the porous medium, and that's what that derivative is. And what it's going to lead to is it's going to lead to a temperature front moving through the pore space. Right? There's nothing else it can do. We will show how to do that analytically. But what it means physically is stuff is moving through the pore space, heating up the rock and the fluids as we go. Okay, that's convection. But then we have this second derivative, and this second derivative is your heat conduction. And just as we said with Fick's law, you know, random motion smearing things out, equilibrating concentration, it's going to do the same with temperature. It's going to smear out the temperature profile. And this is basically conduction, but we'll show that it's effectively a diffusive type behavior. It's basically obeying the same equation as Fick's law of diffusion. Fourier's law is mathematically the same. Conduction essentially gives us smearing out, a smearing out of temperature gradients. You have a large flux where there's sharp temperature gradients. They're going to smooth out the temperature. So basically what happens physically, okay, it's a bunch of symbols on the board here, but what's happening physically is that stuff is moving, so a temperature front is moving through the pore space, and then temperature gradients are basically diffusing out. The temperature is being smeared. And we will see the same if we think about concentration, something, say, dissolved in water. Again, it moves with the flow, and then it diffuses. And in a more complicated and non-linear fashion, we're going to see the same with what appeared to be the simpler equation for mass transport. We're going to see saturation moving through the porous medium and actually a diffusive effect due to capillary pressure. But although the first equation looks simple, the solution is much more complex because it's non-linear. This is actually a linear equation, and funnily enough, is much easier to solve.